Good morning. This video is for North Pontotoc High School's physical science class, if you have me this semester. So what we're going to do is the chapter that we would have gotten to if we hadn't started missing school, which is chapter 8, and it is on solids, liquids, and gases. So I am going to basically just do, if I can find it, similar to how I would normally do in class, just sort of walk you through the notes and talk about them. If at any time you have any questions that you don't understand, feel free to email me on our school email if you don't understand something. So just waiting on this to load. All right, so once again, chapter 8 is on solids, liquids, and gases. The videos that I usually play for you probably will not play for you. So you can see the title of them as we go through. And if you want to just look them up on YouTube and watch them, feel free. So our first section that we're going to do today is 8.1, matter and temperature. So note number 1. There are 4 states of matter: solid, liquid, gas, and plasma. You probably already at least knew the first 3, solid, liquid, and gas. And then plasma is a 4th one that we will talk about a little bit later. So once again, we'll just skip over the videos. Note number 2. The state of a sample of matter depends on its molecular motion as measured by temperature. So in other words, whether something is a solid, liquid, or gas is going to be determined by how fast the molecules are moving around, and that is determined by the temperature. So an example of this would be water. So water exists as ice when it's at a low temperature. Liquid water would be kind of at moderate or medium temperatures. And then when water is in the gas state, water vapor, that's going to be at higher temperatures. So whichever state it is in is directly linked to the temperature that it is. So you can see in this picture also that it, once we look at temperature, then we're going to look at how close the particles are to each other and their arrangement. So you can see in a solid, they are much closer to each other and sort of in a fixed position. So the molecules are still like vibrating, but they can't go from place to place. And a liquid now, they can move around, they can slip and slide and go past each other, but they are still contained in a certain shape in the container. And then with a gas, they're further apart and they can pretty much go wherever they want. We're going to talk about solids first. Note number 3. Every solid has a definite shape and a definite volume. So this means when things are solids, because of how close their molecules are to each other, that's going to keep them in a set exact shape. And they're also going to be in a set volume. So in other words, solids stay the same shape and volume they are no matter what container you put them in. So if you took a little round kid's block and put it in a beaker, it's still going to stay a round kid's block. It's still going to stay the same shape. So you can go through and look at the pictures. So a spoon keeps the same shape whether you put it in a bowl or a glass or leave it on the counter. This is because it's a solid. Under ordinary conditions, you can't squeeze it into a smaller space, so it also has a definite volume. Solids have specific characteristics. The tiny particles are in constant motion, and these make up all matter. And this idea that everything is made of tiny particles that are in constant motion is called the kinetic theory of matter. The particles in solid matter are held very close together by forces that are in between them. And this is why a solid can't be squeezed into a smaller space because it's already really close together. The particles can vibrate against their neighbors, but they can't move around, so they can't get out of their locked-in position. They can't move over or around each other. This is why a solid holds its shape. In most solids, the particles are arranged in repeating geometric patterns. These arrangements form crystals. So sometimes we have an idea in our mind of crystals, what a crystal is, but it's not necessarily something that looks like what you think of as a crystal. Different kinds of solids have crystals of different shapes. So examples, salt crystals are little cubes. A snowflake is a crystal of water. That's a hexagon. Some materials such as glass, plastic, and wax appear to be solids but are not made of crystals. And these are called amorphous solids, and that just means having no form. So some scientists think these non-crystalline materials should be classified as very thick liquids. So I'm not saying that they are, but some scientists think they should be classified as that. So if you'll look at the picture, you can sort of see the difference between the arrangement of a crystalline solid and an amorphous solid. So they're both still solids, but they do have different arrangements of their molecules. So moving on for a quick explanation of liquids. Number 7, a liquid flows and takes the shape of its container. However, like solids, liquids can't normally be squeezed to make up a smaller volume. So they can change shape, but not volume. Although its volume does not change, the shape of a liquid does change, and it depends on the shape of the container that you put it in. Number 8, the kinetic theory explains the properties of liquids. Because a liquid can't be squeezed, its particles are still very close to each other. They do have enough kinetic energy, though, to slip and slide around each other, and this is why they take the shape of their container. So this is why you can pour it from a glass to a bowl to anything else, and it's going to take that shape of whatever you pour it into. Because its particles are held very close together, almost as close as those of a solid, liquid matter does have a definite volume. So if you pour 1 liter of a liquid into a 2-liter bottle, it will not spread out to fill up that whole thing. And also you couldn't force a 1 liter amount of liquid like juice into a 1/2 liter. So it's not going to spread out, or it's not going to squash down. And then we have gases. So gases are kind of what you might think of as springy. This means they expand or contract excuse me, to fill the space available to them, and they can be squeezed into a smaller space. So they can expand out, and they can be kind of squashed down to take up a smaller space. So what this means is the gas has neither a definite shape nor a definite volume. So if you compare the gas with the solid, the gas does have a definite shape and a definite volume. A gas doesn't have a definite shape or a definite volume. So these little particles are going to just kind of keep moving away from each other until they bump into something. Number 11, according to the kinetic theory of matter, the particles of a gas have enough energy to separate completely from one another. The particles can move in all directions. They can spread out completely. And so the movement of the particles and the collisions between them causes gases to diffuse. If you think back to biology when you had that, we studied diffusion. So this is just the spreading out of particles from an area of high concentration to a lower until they are basically spread out uniformly. They'll just keep spreading until something stops them. Also, because the particles are not close together, you can squeeze them into a smaller space. You can squish them. So this is a really cool video if you want to look up and find it on making rock candy and some other things that go along with this lesson. All right, and the last state or phase of matter is plasma, which is kind of the least talked about. And we see this on the sun and in other places in space. So plasma is a gas-like mixture of positively and negatively charged particles. It's not too familiar to us, but it is actually the most common state of matter in the universe because we find it in the sun and in stars. So 99% of the mass of our solar system is contained in the sun, which is mostly plasma. So particles of matter move faster as the matter is heated to higher temperatures. So the faster they move, the greater force that they're going to bump into each other, into other particles, or collide. So as matter is heated to very high temperatures, the particles collide even more violently. And as a result, these particles can actually break into smaller particles that are electrically charged. And this is what's going on with plasma. So although plasma is made of positively and negatively charged particles, the overall charge of the gas is still neutral because the positive and the negative charges balance each other and kind of cancel each other out. And this is what makes up plasma. So you can see the four main phases of solid, liquid, gas, and plasma. You can compare those by studying the picture. So another place that we can see plasma is in fluorescent lights. So when you turn the switch on, electricity causes particles, for example, of mercury gas inside a tube to form plasma. And it's also found in lightning bolts, neon, and auroras. Auroras are super interesting. So if you have the time, you might want to find a video on that project. And then we're going to talk quickly about thermal expansion. So this is just a characteristic of all matter that says it expands when it gets hotter and contracts when it gets cooler. Probably already knew that. So strips of metal that run across floors and up the walls on long hallways of concrete and steel buildings that cover gaps in the building are called expansion joints. And this is going to help as the building heats up and cools down. So expansion joints allow the building to expand in hot weather and shrink in cold weather. And the goal would be that it would not crack the concrete. And another main place that you would see these are in bridges. So you can actually, if you're maybe going under a bridge and look up and see, you can see those expansion joints that help it not crack. So that's a great picture to let you know if you're crossing a bridge and you see that. That's there on purpose, and that is to help the bridge be able to expand and contract safely. There's another example. And maybe you're standing outside the school at break and you notice this vertical area that has a different material than concrete, kind of a smushier material. That's also an expansion joint. One exception to the normal way of thermal expansion is water. Water works opposite. So when water gets colder, when you freeze it, it actually takes up more space. So that is an exception to our thermal expansion rule. The water molecules are unusual in that they have highly positive and highly negative areas. So these charged regions make water act different. As the temperature of water drops and gets colder, the particles move closer together. The unlike charges will be attracted to each other and line up so that only the positive or negative zones are near each other. And because this causes the water molecules to orient themselves according to charge, empty spaces occur in the water, so the water expands when it's going from a liquid to a solid. So when you get ice, that's why it takes up more space than regular water. So solid ice is less dense than liquid water because of this, and this is why ice floats on top of the water, even though they're both water. So you can see the difference. The first picture shows you how the water molecules orient themselves in ice, and the second picture is in liquid water. All right, so that's going to be it for our first section that we're going to do in chapter 8. So let's see if I can go ahead and get this stopped. So stay tuned and I'll present more videos later. I can get this to close.